Okay, let's consider now R3 with this addition operation. We don't have to use just regular vector addition. We can define our own addition operation. And often we use a different symbol for the plus here, but your text doesn't bother to do that, so I won't confuse you by doing that. Although that might be in itself a little confusing. Okay, then we define ABC plus D, the order triple ABC plus the order triple DEF to be A plus F. That's the first one in this one plus the last one over here. And then B plus D and C plus E. Okay, so, you know, you can kind of look at this, and if you think about it a little bit, you're going to be pretty sure it's not commutative. It just doesn't look like things are going to match up. That's where we're going to fall down, and that's what we're going to check carefully. It is closed, though. Clearly, this sum, if A, B, and C are real numbers, D, E, and F are real numbers, you have three real numbers here. So you do have closure. Sum of any two order triples in R3 is an order triple of real numbers. Okay. Now let's look at commutativity of addition. All we really need to do is write this out, and often, especially for the easier problems, that's really all you have to do. You just write it out and test it. You have to know what to write out, but once you write it out, it comes about pretty simply. So the question then would be, and I'm going to use x1, x2, x3, sorry, x1, y1, z1, x2, y2, z2. Instead of trying to do A's, B's, C's, D's, E's, and F's, I'm going to use subscripts. It's just, the notation is much simpler and easier to follow. According to this algorithm, or according to this definition of addition, we would add the A and the F, which would be the first and the last. First from this ordered triple, the last from this. We get x1 plus z2. And then, let's see, B plus D, B would be your y1, D would be your x2, so you have y1 plus x2. And then C would be what? Your z1, and that would be added to E, which would be your y2, so you have z1 plus y2, and that would be the sum on the left. Now let's reverse the two ordered triples and get the sum on the right. Well, we're going to have x, first one plus the last will be x2 plus z1. Already it's different, okay? Already you have an incompatibility, and then we could write out the other two as I did, but as soon as this isn't equal to this, you know that these two ordered triples can't be equal, so it's not a vector space. So I say, yeah, these two aren't equal, neither are the others. This one isn't equal to this one isn't equal to this. And even if one of them was equal, it wouldn't make any difference because they've all got to be equal. Okay, so this is not a vector space. Now, we go to this space R infinity, which is something you need to encounter at some point, so you might as well encounter it now. You get into infinite dimensional spaces of functions, things get real complicated. But for this particular space, where the addition is just going to be the addition of real numbers again, you're going to add each component to the corresponding component of the other, and we'll do that in a minute. It's going to be fairly simple and fairly easy to test the properties. Okay, so we have R infinity. It's a set of ordered, not n tuples, because n would be finite. It's a set of, it's an ordered sequence, an infinite sequence of numbers separated by commas, okay? Never ends. So you wonder how we could even have such a thing. Well, it's easy to define them. I could define one. It could be 1, 1/2, 1/3, 1/4, 1/5, and so forth. It doesn't have to have a rule either. Actually, I guess it kind of has to be a way of identifying the thing, a way of defining it, if you want to define it. But there are a lot of them that wouldn't have any pattern that would make it easy for us to even think about what the definition would be. Okay, you don't have to think too hard about that, although if you've had a good calculus course and look at sequences and series, you have some idea that you can have an infinite sequence of numbers, okay? Now, if I add two of these, okay, so let's call the first one x2, x1, x2, x3, etc. Call the second one y1, y2, y3, etc. Then the addition is just going to be this one plus this one. First one plus the first one, that'll be x1 plus y1. Second one plus the second one, that'll give us x2, y2, and we just keep doing that. So the dots just indicate the pattern is going to continue in the obvious manner. Now, if you reverse these two members of R infinity, you get this, the y's plus the x's. So that you're going to have y1 plus x1 here, and y2 plus x2 here, and y3 plus x3 here, etc. Well, x1 plus y1 equals y1 plus x1, x2 plus y2 equals y2 plus x2 by the commutativity of real numbers. Yeah, this is R infinity. These are all real numbers. So these are going to be equal by the commutativity of addition of real numbers. Okay? Is there a zero vector in this space? Well, what would you add to, say, x1, x2, x3, etc., in order to get x1, x2, x3, etc.? It's fairly obvious that your zero vector would be the ordered sequence, let's say, with all numbers being equal to zero, with all members equal to zero. So it's just this would be your zero vector. If we add that to x1, x2, x3, dot, 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 we're going to get x1, x2, x3, dot, dot, dot. Because 0 plus x1 is x1, 0 plus x2 is x2, etc. So that's fairly straightforward. Now, it's not really easy to always understand what to write down or how to write it down, so you probably want to start thinking about, well, why would this be so? Okay, why would this not be commutative? Okay, I can see why it's not commutative. It doesn't seem like I need to write it down. Well, you do need to be able to write it down, so make your best attempt. I'll be glad to give you some guidance on it. I don't expect miracles right at the start, but I do expect a good effort. And, you know, a good effort might just be, here's how I understand why it is. With a reasonable explanation, we can refine that into a mathematical proof, or at least move in that direction. Okay.